Good afternoon, all. We were studying about the flip-flops, right? So, in fact, we have almost came to a conclusion about the final design of a flip-flop using JK flip-flops with master and slave flip-flops. Now, we have spent considerable amount of time on flip-flops. So, what is the application of flip-flops? Now, before that, currently we are studying about how do you convert from one flip-flop to the other, and what is the objective of studying this particular topic. Don't look at this particular concept as just as a topic. Why we are doing this from conversion of one flip-flops to the other is very simple reason. Say you go to a market for because you have certain kind of application and you want to implement using digital circuit. And in that digital circuit, you are currently looking for some flip-flop. Say for example, you are looking for a T flip-flop, and that can be implemented only using T flip-flop. Now, when you go to the market and you don't find a T flip-flop anywhere of your liking, of your specifications, then always you have an alternative method, which means, say for example, the guy says that, sorry sir, I'm having only SR flip-flop. If you can manage with SR flip-flop, then you can get. That is one reason to study this particular topic of converting from one flip-flop to the other flip-flop. You have only SR flip-flop, you can easily convert that into a T flip-flop if you understand this particular topic. The other reason is, say for example, again, you go to a market and you find that T flip-flop is available, but the cost of the T flip-flop is, say for example, 200 rupees. But the shopkeeper says that I'm having a D flip-flop which just costs you 20 rupees. Then also you can think about why to spend 200 rupees for a T flip-flop. Instead, I can use a D flip-flop for 20 rupees. Just a simple logic conversion will help me convert a D flip-flop to a T flip-flop. These are some of the real-time practical issues. These are some of the practical issues that helps us to study this topic of converting from one flip-flop to the other flip-flop. In the in the last class, we understood what how the converted logic will look like. So which means that if this is the given flip-flop, say if this is the given flip-flop, you will have a conversion logic, and
Sir, you
with the
haven't
required
shared your
inputs, you can
screen.
convert. Hello?
Hello, sir, you
Yes.
haven't
Yeah, yeah.
shared your screen.
Oh, actually, there was a disconnection and then it
Oh,
went off. So just I'm doing it again. Please keep me notified if something you are not getting, because I'm continuously lecturing and speaking. Okay, so just interrupt me. Okay, all right.
okay, sir.
Yeah. Now, what are the steps to do this? First thing that you need is, if you are having a kind of a flip-flop, say let us consider that the given flip-flop to you is flip-flop A and the desired flip-flop is flip-flop B, and you want to convert flip-flop A to B, right? So what are the things that you need to design this logic of conversion? First thing that you need is you need a characteristic table of the flip-flop that you are going to design. Okay, and you need the excitation table of the flip-flop that you already have, which means if you are converting from A to B, you need the characteristic table of B and you need the excitation table of A, right? So this is what it means. Now I'll just show you how to design a JK flip-flop from SR flip-flop, which means that you need the characteristic table of an SR flip-flop and you need the excitation table of the JK flip-flop. Okay, now first let us see how to do it. Now, as I said, that this is how you then once you have these two tables, you are going to club these particular two tables. You will be having an excitation table. You will be having a characteristic table of say SR flip-flop here and JK flip-flop here. And in order to relate these two tables of two different flip-flops, you will require what is the present state of your flip-flop and what is the next state of your flip-flop, Q of t and Q of t plus 1. So this is the one that will link both the different kinds of flip-flops. Your present state and your next state is the one that will link both your excitation table and your characteristic table. Okay, now this is how your truth table will look like. Okay, we will, yeah, this is how your truth table will look like. So for always in the first few columns, you will write the excitation table of the flip-flop that you are going to design. In this particular case, we are going to design a JK flip-flop. So this is what we require. We will be inputting the excitation table data here. And towards the end, normally how do we write our truth table? We write our truth table as inputs and outputs, right? So here the output is going to be through an SR flip-flop. Hence, the given table is towards the end of the columns. Okay, so the outputs will obviously come from the SR flip-flop and the inputs will come from the JK flip-flop. Okay, and the one that clubs the two kinds of inputs are your present state and your next state. Now, this is how your truth table is going to look like. And once you frame this truth table, then what you do is you will write the Boolean expression for the outputs. Obviously, this is how we have been practicing. We will write the Boolean expressions for the outputs. Please note here that SR flip-flop, if you have two flip-flops, then you will have four different types of outputs. You will have SA, RA. If I have one more flip-flop, that is SB flip-flop and RB flip-flop. We will see all these things together. So you will write the Boolean expression for these. And once you write the Boolean expressions, then what you do is you will map that particular Boolean expression into a circuit diagram. So finally, as a last step, you will draw the circuit diagram using the Boolean expressions that you have derived for the S and R in terms of J, K, and your excitation state. Okay. Now, I mean, I have explained you the steps. Now let us do a practical example, then you will understand. Now, this is how your truth table is going to look like. Am I right? So these are your you want to convert from SR flip-flop to JK flip-flop. So what is the wanted, sorry, what is the wanted flip-flop? What is the wanted flip-flop is a JK flip-flop. What is the given flip-flop? Given flip-flop is an SR flip-flop. So always your given flip-flop, through the given flip-flop only you will get the outputs, right? So always this will be towards the end, given flip-flops. And what is wanted, so only through the wanted you will be giving your inputs. So these JK are the wanted flip-flops, and the one that clubs this both the flip-flops are your present state and your next state. Now you will fill up the characteristic table of a JK flip-flop. uh, Quickly let me scroll up to the characteristic table of a excitation table of a JK flip-flop. Can I scroll? Just a minute. Yeah, I'm going to the excitation table of a JK flip-flop. Where is the excitation table? This is SR. And yes, I have this JK table. Okay, so I have to fill this. This is my excitation table. Okay. So I have to fill from here only. Okay. So instead, I will use my state table here. I'm going to use this particular state table. Please look at what are the inputs and outputs of a state table is. Jk is the input and Q of t is again one more input. Q of t plus 1 is my output. So what I'm going to do is, instead, if you just use the state table that I just showed you, you will go wrong. So always don't try to by heart anything here. Always try to apply the logic here. So first look at the first four columns only, right? So this is what is the excitation table. Uh, okay, sorry. This is what is the characteristic table of a JK flip-flop is. First look at four columns. Out of the four columns, these are the inputs and these are the outputs of the characteristic table of a JK flip-flop. 0, 0, 0. Okay. When your inputs are 0 and 0 and your present state is 0, what will be your next state? Your next state will be 0 because there will be no change from your present state and your next state. This is how you have to fill. If you just bluntly by heart and use the characteristic table of a JK flip-flop, you will go wrong. Okay, always apply the logic. When it is 0 and 1, then K equal to 1 corresponds to you are clearing your next state. So despite whatever it is your present state, you will clear your output state. Now, when it is 1 and 0 and your present state is 0, you are resetting your J, so which means that your next state will be 1. When it is 1 and 1 and if your previous state is 0, please remember this is a toggling state. So 0 gets converted to 1. Maybe I will do parallelly the other one also. When it is 1 and 1 here, and if your present state is 1, this is a toggling state in JK, this will reset you to 0. Similarly, when your JK is 0, and if your present state is 1, there will be no change, so this is 1. When this is 0, 1, this will be similar to this particular row. It will clear your next state. When J is 1 and K is 0, despite your present state, it will just reset your Q of t equal to 1. So now you have filled up your characteristic table. If you have any doubt, please stop me. Is this okay? Okay. Now, now you have filled up the first four columns of your characteristic table of a JK flip-flop. Now what you should do is you have to fill the excitation table. Now, whenever you are filling the excitation table, what are the columns that you will look as? Let me clear the highlights. Okay, now what are the columns that you will look as? You will look at the last four columns, which means these are the inputs and these are the outputs, and you will look at the excitation table. I'll just show you how the excitation table will look like for an SR flip-flop. So yeah, this is how your excitation table of an SR flip-flop is going to look like. What does this mean? 0, 0 corresponds to 0x, 1, 1 corresponds to x0. 0, 1 corresponds to 1, 0, and 1, 0 corresponds to 0, 1. This is the reason I asked you to remember this, because these will not be given anywhere in your question paper or something, because unless if you do a mistake here, then every design will go wrong. So that is why I asked you to remember. Now coming back to the excitation table, what does 0, 0 present state and next state 0, 0 corresponds to? It is 0x. Again 0, 0 corresponds to 0x. 0, 1 corresponds to 1, 0. 1, 1 corresponds to x0. 1, 0 corresponds to 0, 1. 1, 1 x0. 1, 0 0, 1. So we fill the excitation table. So for the characteristic table of the required flip-flop, we use the first four columns. For the excitation table, we use the last four columns. So that is why I said that these two columns are the one that links your JK flip-flop and your SR flip-flop. Now, next, what is the next step? You have the inputs and you have the outputs. You write the Boolean expression for this column and the output column, especially the S and R flip-flop. So you will have to write the Boolean expression for yes now, or you find the K-map for the yes. So for yes separately and for R separately, we find out the Boolean expression or the simplified expression. So it is 0, 0, 1, 1, x 0, x 0. Okay. And the other thing that you must note here is we have jumbled our entries here, right? So if you write these entries properly, then these will come as a sequence. I have done a mistake in my notes here. Otherwise, if you write these sequences in a sequential manner, your input combinations in a sequential manner, then you can blindly copy these particular outputs onto your K-map. I have jumbled here, so that is the reason I'm facing difficulty here. What does this mean? 0, 0, 0 corresponds to 0. So I will take some time to fill 0. Now 0, 0, 1. This is not 0, 0, 1 here. I have jumbled. So 0, 0, 1 is here. This corresponds to don't care. So I will fill don't care here. Okay, then next is 0, 1, 1. Where is 0, 1, 1? 0, 1, 1 is 0, 1, 1 is x here. Am I right? 0, 1 and 1 corresponds to 0, right? So this corresponds to 0. Then 0, 1, 0. 0, 1, 0 also corresponds to 0, 0. Then it is 1, 0, 0. 1, 0, 0 I have here, which is 1. So 1 here. Then it is 1, 0, 1. 1, 0, 1, don't care, don't care. And 1, 1, 0. 1, 1, 0 corresponds to 1, 1. And 1, 1, 1 last corresponds to 0. This is how you fill. In case I will not face this difficulty, if I have written these sequences in a sequential manner like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Likewise, if I have filled, then I would not have faced this particular difficulty. So this will be my Q of t, and my Q of t plus 1 will be accordingly like that. So 0, 0, there will be no change, 0. 0, 0, 1, there will be no change. 0, 1 will make my next state 0. This will also be 0. 1, 0 will make it 1, and 1, 0, 1 will make it 1, because I'm not bothered about my present state here. 1, 1, 0. This is going to 1, 1. This is going to toggle 0 to 1, and this is going to toggle from 1 to 0. So this is how my next state will be, and accordingly I will have my SR flip-flop. And if I do this as a sequence, then I would have quickly done this instead of exactly finding the maps. Now, okay, now that we have created a K-map, right? We got the Boolean expression for S and we got the Boolean expression for R. Now we have to, now what is the last step? Draw the circuit diagram using the Boolean expressions derived for SR flip-flop in terms of JK flip-flop. And if you see here that your SR flip-flop, which are the inputs, will be in terms of J and K. Now let us see how to draw the circuit diagram. Now what is the flip-flop we have in hand? We have a flip-flop which is SR flip-flop in hand. And what are the inputs and outputs? S and R are the inputs of the flip-flop, and Q and Q bar are the outputs of your SR flip-flop. Now what is the equation for S input? It is J Q bar. So I'm having a J input here. It is AND of Q bar. So it is Q bar and AND will be fed to SR flip-flop. And what is the input of R? K dot Q. So K is my input and Q is my output from the JK, and of that will go to SR flip-flop. And obviously, since this is a flip-flop, I should not forget this clock. Okay, so your circuit diagram is done. Now, if you look at the overall picture like this, a dotted diagram, right, taking the outputs exactly, this is nothing but a JK flip-flop. This is nothing but a JK flip-flop. So what we have done, we have converted an SR flip-flop to JK flip-flops. Our inputs are JK and outputs are Q and Q bar. From where? From an SR flip-flop with inputs S and R and Q bar as output. Is there any doubt here in complete design? Okay, similarly, you can do multiple exercises. right? You can convert all possible combination. You can convert JK to SR, JK to D, D to SR, D to JK, D to T. Likewise, you can do, and these are the Boolean expressions for that also. I have given you the solutions also. Maybe you can try. Maybe for one or two, I will draw the truth table. So let us look at the solution of this, just the truth table of this. Okay. So we have to write the characteristic equation of S and R. So this will be the characteristic equation of S and R. Here I have done it rightly. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and correspondingly what is the next state, you can fill this particular column. And the excitation table of a D flip-flop, this will be the excitation table of a D flip-flop. We all know that D flip-flop is not dependent on the present state, it just depends on the next state. So 0, 1, 1, 1, 0, 0, 0, 0. We just copy our next state uh, inputs to our D flip-flop inputs. Similarly, for the fourth example, if you want to convert a D flip-flop to JK flip-flop, so this is how you convert, and this is the truth table, right? And the circuit diagram also I have given for converting a D flip-flop to an SR flip-flop. Similarly, the last example, D flip-flop to, so because I have an equation here, if I want to convert D to SR, the D equation, because this is the output, right? I will be writing the Boolean expression for the last column. So D is given as S plus R bar Q. So how will the circuit will look like? I am having a D flip-flop. It is S plus R bar Q, right? So I take the output of Q here and I AND it with R bar. If you don't want R bar, then if you want just have R, then you put a not here. Okay, so this will be R bar now. And then it is R'd with the S input and fed to a D, and this converts D flip-flop to an SR flip-flop. Any doubts here in conversions? Because next we are going to move on to the real applications of the JK flip-flops. Okay, good. Now, whatever we have seen so far is about how to use the flip-flops effectively. If you don't have one kind of a flip-flop, obviously you can implement the available flip-flop and convert it to a required flip-flop. Now, where are the applications of these flip-flops? Normally, these flip-flops are used in sequential circuits. What do you mean by sequential circuit? Anything that performs sequentially is a sequential circuit. Okay, I'll give you a simple case study. Say, for example, you want to count the people, the adult people who are entering a cinema theater, and you don't want to count the kids. In that particular case, this is a you can implement this particular case in a digital logic circuit. And what is the digital device that you will use is you will use a flip-flop. Please note here, I'm just saying in general a flip-flop. It is you can use any flip-flop that you have. You can use a D flip-flop, you can use an SR flip-flop, T flip-flop, or JK flip-flop. It is up to the designer's choice. Whichever is cost effective, you can, whichever is faster, whichever has got a less logic to implement, you can choose any kind of flip-flop that you want to implement. Okay, now we are really jumping into the applications of the flip-flops, which is nothing but the sequential circuit. Now, as the name implies, the sequential circuit, everything operates in sequential manner. What does this mean is, after one action is done, the next action will be done only after an external input. Okay, say for example, you want to design, if you are counting in a basketball game, right? You can place a sensor in the, if say for example, this is what is the basketball, what do you call the basket, right? Where you will be placing your ball here, right? You place a sensor somewhere here, right? You place a sensor somewhere here. So the objective of this particular sensor is whenever ball crosses this particular basket, it has to increment. You have a scoreboard, right? say two teams, some A team and B team. Whenever A team puts a ball in their basket, B team will take that ball and throw it to C team. Whenever there is an internet failure here, so I'm just trying to reconnect through my laptop. So just please hold on. Right now I'm through mobile. Okay, I think I'm audible. Yes. All right. So this is an example of a sequential circuit. Now let's go through what are the steps that we need to design such kind of a circuit? Let us assume that I'm going to implement an application, something like this. So what is the design procedure or what is the analysis procedure? Now, so what we will see next is analysis of a sequential circuit. In fact, and the better word to use here is instead of analysis, we should use design of a sequential circuit. So what do you mean by analysis? Analysis means you are having a particular circuit uh, which will perform under a particular condition, and you have to understand the behavior of that particular circuit. When you say understanding the behavior of the circuit, what does it mean is, it means that say you are giving a, how does your inputs, outputs, and different states of your flip-flop move whenever you are giving a clock. Please remember that. Let me jump directly to this particular circuit. This is a simple sequential circuit, which is implemented using a D flip-flop. Please see here that there are two D flip-flops here. One is D flip-flop A and D flip-flop B. When I say analysis, what does it mean is, for every clock input, please remember that the only controlling input here is the clock input. So for analysis means, for a given clock input, what is the state of these two flip-flops? When I say state, say what is your present state, what is your next state of this A flip-flop. Similarly for this B flip-flop. Then what is your inputs and how your inputs are actually affecting your present state and your next states. These are the things that I will look at whenever I'm analyzing a sequential circuit. So the behavior of clocked sequential circuits is determined based on the inputs, which in this particular case is X here, outputs, which in this particular case is Q and Q bar, and states of the flip-flop represents that, which in this particular case is Q of T of A flip-flop and Q of T of B flip-flop. Okay. Now, so this is what is required. Now I'm slowly jumping on to what are the required ingredients for this design. Say you want to cook a pizza, then it is not that you must understand what is the procedure, right? You must have the required ingredients also. Here also, to design any sequential circuits, what are the ingredients here? You will require first, always we are going to do a reverse engineering here, which means you will be given some kind of a circuit like this. You have to do a reverse engineering and find out what are the inputs and what are the possible outputs. Okay, Japanese are very good at reverse engineering, right? After this atom bomb issue, that they all did was reverse engineering. Now Chinese are effectively doing, but uh, and even Chandni Chowks are very good at the reverse engineering thing. Okay, so we are going to do the same thing here. We are not good, but we are not going to do jugad here, but we will do a proper design. So from the circuit diagram, right? So you are given a circuit diagram here. From this circuit diagram, we will derive a state table. Once you create a state table, we will derive a state diagram. Now, in order to derive the state diagram, you will require, in addition to this, you will require a state equation also. Now, where do you get the state equation? We already know the Boolean expressions for whatever the flip-flops that we have studied. We have studied the characteristic equations, right? For various flip-flops, SR flip-flop, DT, and JK flip-flop. So we will use those state equations also. So we will require the state equations to be derived for the flip-flop inputs as well as the output functions for the circuit. And we will require what is the present state and the next state for designing this. So an example of a sequential circuit for D flip-flop is given here. Now, first we are going to see one by one. Okay, so the all our ingredients. I mean, it is something like if you need a pizza, I'm just going to explain you what kind of bread you will use, what kind of pizzas, sorry, the cheeses that you will use. So I'm just something similar to that. I'm going to explain here. What do you mean by a state equation, right? And the behavior of your clocked sequential circuits, we are going to describe only algebraically using the state equations. Whenever we say that we are going to analyze the sequential circuits, we are going to look at the behavior of these clocks only, right? So we will be describing the behavior of these particular clocks based on an algebraic equations. Now, what do you mean by a state equation? The other name of the state equation is called as a transition equation. Why we call it as a transition equation? Because that is the one that will relate your present state to your next state and next state to your present state. Okay, so which means if you are using a D flip-flop, we will use the state equation for a D flip-flop. If you are using a JK flip-flop, we will use the state equation for a JK flip-flop. Likewise. So a state equation is an equation which specifies the next state as a function of your present state and the input. In this particular diagram, your input is X. So your next state output will be as a function of present state and your input X. Now, let us consider the given sequential circuit here. For that, this particular sequential circuit that we have given, what are the state equations? Now, what are the inputs of a D flip-flop and what are the outputs of this particular circuit diagram? The inputs are, let me erase the inks and highlights. Okay. Now, what are its input? X is an input. What are its output? A bar, B bar. Why is it A and A bar? Because it is coming from A flip-flop and B flip-flop. Please always remember, do not combine different kinds of flip-flop. Okay, this as D and this as JK, then you definitely you cannot implement such kind of a logic. Okay, so always if you are choosing one kind of a flip-flop, then everything will be of the same kind. So, and the other outputs. So Y is an output here. Okay, so this is an input, this is an output. We do not really require these output, but these are required for our understanding because these gives us our next state outputs from these flip-flops. At the same time, there are more inputs here. There is an input here. There is an input here to this flip-flop, which is nothing but the present state inputs of these particular. So to summarize, what are the things that we need is we need input, we need output, we need present state, and we need next state. Okay. So for the sequential circuit that is given, it has got two flip-flops, A and B. It has got an input, it has got an output. Okay. And the D flip-flop inputs are determined by the next state, which is governed still further governed by the state equations. Now, what is the next state of the two flip-flops? We have two flip-flops. Remember, A and B are the two D flip-flops we have. So the next states are A of t plus 1 and B of t plus 1. Your present state is A of t and B of t. Always we will write the state equation. I just explained you what is a state equation or a transition equation is. State equation is written as described as a next state in terms of the present state and your input. So in this particular case, for the diagram that I just showed you, your state equation will be A of t plus 1, which is a next state, and B of t plus 1, which is a next state, which will be as a function of the present state A of t and B of t, or at times the combination of anything, A bar also. Along with that, the input X of t, X of t. At times you might have an input, at times you might not have an input. So this is the Boolean expression that specifies your present state and your next state that makes your next state equal to 1. And this combination is called as the state equation. Okay, now all it is always very difficult for us to write every time t plus 1, t plus 1, right? So, but we must be very clear that this t represents that the clock transition. Okay, for every clock transition, there will be a change in your next state for a corresponding change in your input and your present state. So instead of writing like this in a compact form, we can write our next state in terms of the present state just as a dot x plus bx plus a bar of x. Sorry, for for the next state just as a bar of x. So this is for the outputs of a D flip-flop. This is for outputs of D flip-flop. Now there is one more output here, right? There is, what is the output? there is one more output, which is the actual output of our sequential circuit Y. Okay, so the expression for Y is given like this. Please remember what is that we are doing now. In case you lost track of what we are doing, we are trying to analyze a sequential circuit. What is that we are trying to do is we are trying to analyze a sequential circuit. And what is the procedure is you will be given a sequential circuit. And from the sequential circuit, we are trying to go back and find out what are the state equations, what are the state diagram, and what are the present states and the next state. So in order to do that, first we understood what are the inputs, what are the outputs. Okay, then first we started off with the flip-flops. We wrote the state equations for these flip-flops. So for these particular flip-flops, we just wrote the present state. So a of t plus 1 can be given as a of t dot x of t plus b of t x of t. Where did I write? How did I write this? I wrote the equation for this line. Where it is coming from? It is coming from this, right? And this is added together. What is this? This is q and this is q and this is x. So this is q dot x. And what is this particular line? This is again x. And this particular line comes from where? This comes from b, right? So what is this particular line? It is b dot x. And r q of t now will be equal to q dot x. Sorry, I should not write q because it is from a flip-flop, right? It is a dot x plus b dot x. Is it the same equation? A of x, a dot x plus b dot x. Now similarly for b, let me erase the inks. Okay. Now similarly, let me write for the input for my b flip-flop. So this is AND of something, and where this is coming from? This is coming from a bar. So this line is a bar, and this line corresponds to x. So d input, which is nothing but b of t plus 1 input, is going to be b dot, sorry, x dot a bar dot x. So that is how I wrote this equation, a bar dot x. Now I've got the Boolean expression. Please remember we are doing reverse engineering here. Okay, so we have got the Boolean expression. Now how do you write the output equation? Similar manner. Output here is AND of something, and it is not of what? This is x here, is x bar. So I have an AND of x bar, and this is OR operation of what is this particular line? This particular line goes from here. So this line is going to be B, and this comes from A. Okay, this is A plus B. So multiplied by A plus B. Okay. Yeah. So this is nothing but A plus B multiplied by X bar. Okay, now I have written the Boolean equations. Now I'm going to create a state table. Now what is this particular state table is? The state table will give you the time sequence of your inputs, outputs, and the different states written in a state table. And this is also called as a transition table. Please remember these small names, that this equation is also called as a state equation or a transition equation. The state table is also called as a state table or a transition table. The state table, what does it consist of? It consists of the present state. What is that? It is q of t. It consists of next state, q of t plus 1. Or in this example, A and B inputs, and next state corresponds to A of t plus 1 and B of t plus 1, and its output is given as Y. At times, you might have flip-flop inputs also. The flip-flop inputs is optional. If you want, you can have, else you need not have. And the other thing that is important for a state table is you have to decide on how many flip-flops and how many inputs they will have. Always any doubts because something was flashing. Okay. Okay. Now always, how do you decide the number of rows is, you will always decide the number of rows based on the number of flip-flops you have and the number of inputs that you have. Say for example, in the previous case, we had only one input X and the flip-flops that we had was two flip-flops. So which means it is 2 power m plus 1. So one input, I don't know what is it blinking very often. Okay, there is some parallel meeting going on and notification from that. Okay, so okay, so your input is 1 and the flip-flops that you have is 2. So it is 2 power 3, which means you will have 8 rows in the state table now. So quickly let us see how to create a state table. So this is how your state table will be. You will have the present state, you will have the inputs. Please remember here, now this is going to be the combination and the outputs will be your next state and its output. Please remember this is A of t plus 1 and this is B of t plus 1 and this is going to be A of t and B of t. So again, let us list all the binary combinations here 0, 0, 0, 0, 0, 1, 0, 1, 0 likewise. Now the next state, how do I fill this? How do I fill the next state is we will use these equations. Using these equations, we will fill A of t plus 1, B of t plus 1 and Y. Okay, so right, so we have filled this. Maybe let us take one example here. Let us take this example here. What is A of t plus 1? A of t plus 1 is ax plus bx. Okay, so a dot x is 0 plus 0 dot 0 is 0, hence 0. Now what is b of t plus 1? B of t plus 1 is a bar into x. So a bar will be a bar into x will be still 0, it is 0. Y is ax bar plus bx bar. So x bar will be 1, a plus b is 1, 1 plus 0 is 1, 1 plus 1 is 1 dot 1 is 1. So it is 1. Okay, so likewise, you fill the next state equations. So that's what this has been written. List all binary combinations. You will fill the first 3 columns and in the next output columns, you will fill using the equations. Okay, so if you are using a D flip-flop, you will see that the outputs and in the inputs and the outputs are the same. Okay, so since this is a D flip-flop, it is very, very simpler. If it is a JK flip-flop, then you must use your knowledge on your excitation table. Okay, we will do that example also. Okay, so since this is a D flip-flop, your inputs and outputs, your next states are same, which means that your next state, your A and B, they are same as that of your present state. You see here, the 0, 0, 0, 0, 0, I'm sorry, 0 and it should be the other ways. Okay, so there's some mistake. Okay, all right. Now, there is another way of creating the same state table, right? Though the state table is okay, but this does not really gives us a complete picture. So there is another way of filling the truth table here. How you can fill the truth table is this will reduce our number of rows also. You have the second form of a truth table is you have a present state and you have a next state. Okay, and you will have an output also, which means we are going to use present state and next state and output for different values of your inputs, for different values of your input, which means when your present state is 0, 0, you have either your inputs are 0 or your inputs are 1. When your present state is 0, 1, your inputs are either 0 or it is 1. On that particular basis, we can simplify the 8 rows into 4 rows, something like this. So when AB, when your input is x equal to 0 and x equal to 1. So how did I fill this is when your present state is 0, 0, when your x is 0, your next state is 0, 0. When your present state is 0, 0, When your input is 0, your next state is 0, 0. And when your input is 1, it is 0, 1. Yeah, it is 0, 0 and 0, 1. When it is 0, 1 and when x is 0, it is 0, 0 and 1, 1. When it is 0, 1, it is 0, 0 and 1, 1 for x equal to 0 and x equal to 1. All right, so we fill up this. Likewise, we fill up the output data also. Now, once you have because it is always easy for you if you have in the second form to create the final state diagram. Okay, so finally one form may be preferable better than the other depending on the applications, right? So now how do we draw a state diagram, and what is a state diagram? State diagram is a graphical diagram that clearly makes you visualize how the inputs are changing. And how do we draw the state diagram is all the states are represented by circles. I will be taking some more time today because I would like to complete this state diagram at least till this particular point. Okay, so I'll not go through the all the theory part, but I'll quickly do it. Okay, now what is a state diagram? State diagram is a graphical representation of the state table, right? The state table that you drew here, the state diagram is a graphical representation. Normally, your states, whether it may be a present state or your next state, they are determined by circles. Okay, and the transitions are determined by a directed line or a solid lines. You see in this diagram here that these are the states 0, 0, 0, 1, 1, 0 and 1, 1 are the states, and the state transitions are determined by the directed lines here. You see an arrow mark also here. These are directed lines. Okay, now the state diagram, they gives you the same information as that of your state table. It's not a static table, it's a state table. Okay, now these directed lines now, they are labeled with two binary numbers separated by a slash. You see here that they are labeled by two binary numbers separated by a slash. The first number, this corresponds to the input and this corresponds to the output. Okay, so that's what it means. They are separated by a slash. Input value during the present state is labeled first, and after the slash, output during the present state is given as the input. Now the directed line from state 0, 0 to state 0, 1 is labeled 1, 0, means the sequential circuit is in the present state 0, 0 and the input is okay. I'll explain this, no need to go about this. Now how do we draw the diagram? Okay, now look at this state table here. Okay, my present state is 0, 0. Okay, when my input is 0, when my input is x equal to 0, to which state I am moving? I am moving to 0, 0. I mean, I'll draw here, that will be better. My present state is 0, 0. Okay, when my input is x equal to 0, I am still in the same state. So I will draw a directed line like this with my input 0. At the same time, what is my output? My output when x equal to 0 is 0. So I will put a slash and write 0 here. When my present state is 0, 0 and my input is 0, 1, I'm moving to a state called as 0, 1. I'm moving to a state called as 0, 1 when my input is 1. And what is my output at the same state? My output, I have to look here. My output is 1. Now, when my input is, my present state is 0, 1, that is in this particular state. When my x is 0, I'm going to x equal to 0, 0. So I'm going back to 0, 0 when my input is 0 and at that particular time my output is 1. I look here and write. Again, when it is 0, 1, when my x equal to 1, I am moving to a new state. When my x is equal to 1, when I'm moving to a new state called as what? 1, 1. And at that time, what is the output? I look here and write my output is 0. Understood how am I writing? Likewise, I fill up, and this is our state diagram. Okay, please remember that there is no difference between a state table and a state diagram. It's only the visualization, and this is what we were striving for, to design a sequential circuit. Okay, I think yes. All right. So any doubts till this? So this is, I mean, you can fill it up. Maybe we will take one more case for 1 1, so you will understand better. We will take the last case. 1 1 we will take. When my input is 0 0, I'm moving on to which state? 0 0. So I move on to this 0 0 when my input is 0, and at the same time, what is my output? My output is 1. And when my input is x equal to 1, I'm moving to 1 0. I'm moving to a new state 1 0 when my input is 1, and at the same time my output is 0. I look here and write, right? I hope you can fill it up, right? So this is how I draw a state diagram. Okay, and now the important thing is, how did we, again, let me recall, how did we started and how did we end it? So this is very important. We started from the circuit diagram given. We wrote the Boolean equation, the state equations, or the transition equations, and from the transition equation we drew the state table, and from the state table we drew the state diagram here. The reverse also, it is possible. That is, you will be given a state diagram, you must create a state table, and from the state table you must create a state equation, and from the state equation you must be able to draw the circuit diagram, sequential circuit diagram. Both the designs we will be seeing in this class. Any doubt? Anyway, we will touch upon in the next class and then we will continue. Okay, if there are no doubts, we will disconnect. So thank you so much.